For a really long time, researchers have persuaded us that the universe is continually growing. This conviction has captivated researchers and scholars who have adopted the theory of prehistoric cosmic detonation as the most generally accepted explanation for the beginning and expansion of the universe. According to this hypothesis, the universe began in a very dense and hot state and has since gone through continuous development. However, the James Webb Space Telescope has made an astonishing revelation that challenges this hypothesis. How did the Space Telescope challenge the idea of the universe's expansion, and what does this mean for how we interpret space? Join us as we investigate the new, stunning find from the amazing James Webb Telescope. If you're keen on staying up to date with news from the universe and its environment, subscribe to our channel, like this video, and turn on the notification bell. Albert Einstein's general theory of relativity provides a framework for understanding how the presence of heavy objects curves spacetime. According to this theory, the universe began as a singularity, a point of density and temperature, roughly 13.8 billion years ago. According to the Big Bang hypothesis, all matter and energy were compacted into a tiny, hot region. At that moment, the universe began to grow through a rapid and violent event known as the Big Bang. During the first few moments following the Big Bang, the singularity underwent a massive release of energy. The universe was filled with a very hot, dense, and fiery plasma containing protons, neutrons, electrons, and their antiparticles. As the universe cooled due to its expansion, the temperature decreased enough to allow electrons to bond with protons and form neutral atoms. This process, known as recombination, allowed protons to move freely through space, resulting in the cosmic microwave background radiation that we can detect today. The expanding of spacetime itself may explain the expansion of the universe. This expansion doesn't imply a movement through space where objects move away from a central point, but rather an expansion of space itself. We can imagine it as the surface of a blowing-up balloon. The points on the surface move away from each other not because they are moving, but because the space between them is growing. Similarly, in the case of the universe, galaxies and other celestial objects are pulled apart by the expansion of space, rather than moving away from it. So, what is the source of this expansion of spacetime? According to science, researchers theorize that dark energy is a mysterious type of energy thought to permeate all space and apply negative pressure. This dark energy is believed to be the cause of the accelerating expansion of the universe in recent years. Observations have uncovered a phenomenon essential to understanding the significance of dark energy, the equilibrium between gravitational forces and the expansion of the universe. Gravity, an attractive force acting on massive objects, attempts to slow down the expansion of the universe. If the universe were made entirely of matter, such as galaxies and their corresponding mass, gravity would eventually stop the expansion and lead to a phenomenon known as the Big Crunch. However, observations reveal that the expansion of the universe is accelerating, rather than slowing down. This suggests the presence of a mysterious force that counteracts gravity's effect. This force is produced by dark energy, which is uniformly distributed in space and applies negative pressure. The exact nature of dark energy remains one of the greatest mysteries in modern cosmology, and researchers are actively investigating its properties. Although dark energy is responsible for the accelerating expansion, the distribution of matter in the universe also plays a crucial role. The density of matter and energy impacts the shape of spacetime through the equations of general relativity. Regions with higher density exert a stronger gravitational force, which slows down the expansion of the universe. Conversely, regions with lower density experience weaker gravitational attraction and contribute to the overall expansion of the universe. Matter in the universe is not evenly distributed but is organized into massive cosmic structures, such as galaxies, clusters, and superclusters, which are interconnected by vast, cosmic web-shaped filaments. These structures form due to the gravitational collapse of areas with higher density, influenced by gravity. As the universe expands, these cosmic structures experience an expansion of spacetime. However, gravitational forces within these structures somewhat counteract the expansion, resulting in a complex relationship between the expansion of spacetime and the gravitational influence of mass. On larger scales, the expansion outweighs everything else, resulting in a continuous expansion of the cosmic web. It is important to note that the expansion of the universe does not mean that galaxies are moving away through space. Galaxies may, in fact, come closer together on smaller scales due to the effect of gravity. However, on a larger scale, the overall effect of the expansion is to increase the distances between galaxies over time. Different observations provide abundant evidence for the expansion of the universe. One significant example is the redshift of light emitted by distant galaxies. As the universe expands, the wavelengths of light from these galaxies are stretched, shifting toward the red end of the electromagnetic spectrum. This phenomenon, known as cosmological redshift, provides undeniable proof of the expansion of spacetime. Another key piece of evidence is the cosmic microwave background, CMB, radiation, which is a remnant of the hot early universe. The CMB shows a surprisingly uniform distribution of energy across the sky, with small fluctuations that reveal crucial information about the initial conditions and subsequent development of the universe. Extensive CMB studies have confirmed predictions of an expanding universe and reinforced the Big Bang theory. Observational data from large-scale surveys, such as the Sloan Digital Sky Survey and the European Space Agency's Planck satellite mission, have provided precise information in recent years about the expansion rates of the universe and the distribution of matter and energy within it. These discoveries have improved our understanding and contributed to the ongoing search for answers about the underlying nature of the universe. One of the most fascinating aspects of the James Webb Space Telescope's observations is its ability to map the large-scale structure of the universe at high redshifts, when galaxies were still young and gathered into massive clusters known as protoclusters. These protoclusters are the ancestors of today's galaxy clusters, which are the largest gravitational structures in the universe. By studying these protoclusters, we can learn about the relationships between galaxies, their interactions with their environments, their evolution and merging processes, and how they influence star and planet formation. Protoclusters are extremely interesting but difficult to find due to their wide spread and low surface brightness. James Webb Space Telescope's wide-field, high-responsiveness cameras make it conceivable to recognize many systems in a solitary perception, covering a huge part of the sky with phenomenal profundity and detail that has never been seen before. Space experts can recognize protoclusters by dissecting cosmic system thickness, spectral properties, and spatial scatterings. To do this, they combine information from the James Webb Space Telescope with other observatory studies. The James Webb also provides data on the majority of ages, star formation rates, dust content, and gas kinematics of individual systems inside protoclusters. These perceptions will uncover the differences between systems inside protoclusters and those in less dense conditions, as well as their development over time within their host structures. Additionally, the James Webb will allow us to investigate the intergalactic medium, IGM, around protoclusters, which is affected by supernovae and dynamic cosmic cores. The IGM regulates system formation by providing gas for star development and pulling it out through winds and surges. However, pictures caught by the James Webb Space Telescope are challenging the theory of how things came to be, as they show galaxies of gigantic sizes that appear not to have been able to exist or are not consistent with the theory of the universe's origin. These candidate galaxies are estimated to have formed roughly 13.3 billion years ago, somewhere between 500 and 700 million years after the Big Bang. Astronomers had expected to observe youthful, small worlds around this time in the early universe. However, pictures captured by the Space Telescope reveal that these galaxies might contain about the same number of stars as our own Milky Way galaxy, instead of finding small, young galaxies. This finding shows mature systems, like our own, in what was believed to be the beginning of the universe. The James Webb Space Telescope is equipped with infrared sensors capable of detecting light emitted by older stars and galaxies. This allows space experts to look back in time nearly 13.5 billion years to the beginning of the known universe. Before this discovery, researchers had identified various universes in the oldest areas of the universe, roughly 350 million years after the Big Bang. Using data gathered by the James Webb, these distant heavenly systems were small and in accordance with the expectations of current cosmological models. However, the recent discovery of 6 mature, massive universes in the same region of the early universe raises the possibility of testing current cosmological theory. It may require adjusting what has long been considered accepted scientific knowledge. It is astounding to believe that the early universe might have organized itself so rapidly, as these galaxies did not form at that time. These new revelations arise from studying a region near the constellation Ursa Major, which was first observed by the Hubble Space Telescope during the 1990s. The candidate galaxies are so striking that they contradict most of the current cosmological forecasts. According to current computations, there should not be enough material to form large heavenly systems 500 to 700 million years after the Big Bang. The scientists believe that to explain the observed mass of these galaxies, it would be necessary to either alter current cosmological models or amend our scientific understanding of how galaxies emerged in the early universe. Both speculations require a key change in how we might interpret the early formation of galaxies in the universe. These startling objects have been humorously named universe breakers, and they have so far lived up to their name. Although more data is needed to confirm that these candidate galaxies are as large and old as they seem, the data suggests they are likely to be real galaxies. There's the possibility that some of these objects are massive, yet unseen black holes, which is another intriguing aspect to consider. However, the amount of mass found suggests that the known mass of stars at this phase of the universe is based on multiple times more than previously thought. Although the sample is small, it is still a remarkable difference. It is possible that these objects are not galaxies at all. Another possibility is that they are other types of strange objects, like faint quasars, which would be very interesting. Even if only one of these galaxies turns out to be real, it would have a significant effect on how we interpret the limits of our cosmological understanding. Meanwhile, preliminary observations offer powerful insight into how the James Webb Telescope could eventually alter our interpretation of the universe. The rapid pace of discoveries made by the James Webb is reminiscent of the early days of the Hubble Space Telescope, which was launched into low Earth orbit in 1990. The Hubble Space Telescope quickly began to provide a much more complex image of the early universe than researchers had initially expected. Researchers have made another discovery that challenges the idea that the universe is expanding at the same rate in all directions. This finding projects uncertainty on the widely accepted hypothesis that the expansion rate is uniform in all directions. A new study, based on data from the European Space Agency's XMM Newton survey, NASA's Chandra, and the German Rosat X-ray observatories, revealed that this cosmological theory might be incorrect. A PhD specialist in cosmology and astronomy at Bonn University, along with his advisor, set off on a mission to explore the theory of isotropy. According to this theory, the universe has the same properties in all directions on large scales with little deviations, generally acknowledged as a result of established fundamental physics. This theory has been supported by observations of the cosmic microwave background, CMB, which is a direct remnant of the Big Bang and reflects the universe in its early stages, about 380,000 years old. The uniform distribution of the CMB across the sky implies that the universe expanded rapidly and consistently in all directions during those early times. However, in the present universe, this might not be true. The scientists studied the behavior of more than 800 galaxy clusters in the present-day universe, in collaboration with partners from the University of Bonn and Harvard University. If the isotropy hypothesis were correct, the clusters should have uniform properties across the sky. However, they observed significant differences. They examined data from X-ray temperature readings of the very hot gas found in the clusters, alongside the brightness of the clusters on the sky. One would expect clusters with similar temperatures and distances to appear equally bright. However, this is not what they found. They discovered that clusters with similar properties and temperatures appeared less bright than expected in one direction of the sky and brighter than expected in another direction. These differences were quite significant, approaching a 30% variation. Moreover, these variations were not random but followed a distinct pattern depending on the direction in which you looked at the sky.